Let's go over lesson 4, the library of functions and transformations of graphs. Lesson 3 was about functions. We learned function notation, how to find the value of a function. In this section, we're going to talk about the graphs of functions and how to shift those graphs, particularly left, right, up or down, flip it upside down. That's the transformations we're going to be talking about. Some functions we encounter so often that we expect you just to know their general shape. In calculus, you get to use a graphing calculator, but if you don't know the basic shape of the graph that you're entering on the calculator and you make a typo, you're not going to know it because you don't know what the graph is supposed to look like. That's why in college algebra and in pre-calculus, we focus on this library of functions. And then when you're using a graphing calculator, you'll be able to know when you might have made a typo or when you need to zoom out to see more of the graph or zoom in or something. All right, so our basic functions. The first one is our constant function, f of x equals some constant. The domain of that function, and remember domain means anything, any value of x for which the function is defined. I made an example here, f of x equals 3, and that function is defined for any value of x. No matter what value of x you put into the function is going to spit out a 3. So the domain of that function is negative infinity to infinity. And if you don't already know what the graph of f of x equals 3 looks like, you can make a table. Now, after a little bit of practice in tonight's homework, you won't have to make tables anymore. We're trying to get away from making tables by just knowing what the shape of these basic library of functions are. Play like I didn't know what that graph looked like, and just eeny, meeny, miny, mo, pick some x's. I see it say negative, or I say eeny, meeny, miny, mo, but my choices really aren't random. I'm going to choose some negative x's, some positive x's, 0. And this function tells me that for any value of x, this function value or y value is 3. So y is 3 no matter what x is. And to graph that, I'm going to just graph those ordered pairs. Negative 2, 3, negative 1, 3, 0, 3, 1, 3, 2, 3. And then I remember, oh yeah, the graph of f of x equals a constant, or that's the same as y equals 3. And we know the graph of y equals 3 is a horizontal line. If you don't remember that from Algebra 1, we'll be revisiting it soon. All right, the identity function is just the f of x equals x function. And in the place of f of x, we could always put y, the y equals x function. The domain of that function, anything you can let x be, well, you can let x be anything in the whole wide world. The domain is negative infinity to infinity. So you can choose any x's for your table. Again, my choices really aren't that random. I'm usually boring and stick with negative 2, negative 1, 0, 1, and 2, as long as I can use those x values, as long as they're in the domain. And the identity function is just saying whatever x is, y is the same thing. So when x is negative 2, y is negative 2. When x is negative 1, y is negative 1. When x is 0, y is 0, and so on to finish your table. To see what that graph looks like those ordered pairs. When x is negative 2, y is negative 2. When x is negative 1, y is negative 1. When x is 0, y is 0. Then 1, 1, 2, 2. That's just a line. Goes forever left and right. Put your arrows on there because the domain is negative infinity to infinity. The identity function, we're also going to call that a linear function when we get to section 2.3. Actually, we've already used the word linear in section 1.1. We said a first degree function, y equals x to the first, is a linear function, and the graph of a linear function is a line. The third function in our library of functions is f of x equals x squared, or you could write that y equals x squared. And its domain is also negative infinity to infinity. You can square any number in the whole wide world. So pick your favorite x's. You don't have to be as boring as me. Pick your favorite x's, and I'm really not trying to be boring here as much as I am getting a good sample of different things x can be. I like some negative x's, some positive x's, and 0. That usually gives me a pretty good picture of the graph. I'm going to square each of these values because I'm putting them into the squaring function. -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And then I'm going to plot those 5 ordered pairs. By the way, anytime you're graphing, for me, on a test especially, if you don't label your tick marks, I assume you're counting by 1. You can assume that these are counting by 1. But if I had f of x squared plus 100, I may make my tick marks counting by 10 on the y-axis. If you're counting by anything other than 1, make sure that you label a couple of tick marks on both axes so I know what you're counting by. Otherwise, I'm going to assume it's 1. These ordered pairs, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. That's a nice smooth U-shaped curve. And you may remember that the name of that nice U-shaped curve is a parabola. We'll be graphing parabolas in more detail later, but for right now, I'm just going to say this is a quadratic or second degree function, and the graph of a quadratic function is a parabola. Fourth function, the square root function. What's its domain? What are the x values for which this function is defined? Can I, like I've done in the previous examples, let x be -2, -1, 0, 1, and 2? Actually, I can't. I can't take the square root of -2 without writing it as an imaginary number. Square root of -2 is not a real number. So what is the domain of that function? The smallest thing that I can take the square root of and get a real number. It's 0. And so when I write the domain, I'm going to use bracket on 0 because I can take the square root of 0 and say I can take the square root of infinitely big x values. So the domain of that function is from 0 to infinity. When I make my xy table, I can start at 0, and then I can choose any x values bigger than 0. I'm going to choose ones that are perfect squares, so I don't have to use my calculator to take the square root. My first few perfect squares are 1, 4, 9. If I wanted to go all the way to 16, I could. Take the square root of each of those. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. And then plot those ordered pairs. I'm not going to go all the way out to 16 on my x-axis. I'll just go out to 9. Zero, 0, 1, 1, 4, 2, 9, 3, 16.4 would be off my page. But I can tell that the graph looks like half of a parabola turned sideways. I'm going to call it top half of a sideways parabola when I need some words to describe the shape that I'm expecting. Top half of a sideways parabola. Here's the whole word parabola. Actually, we saw both of those graphs in our lesson 3 notes. We saw y equals x squared and said that it is a function. It passes the vertical line test. No matter where you put the vertical line, it only touches the graph once. If we turn that whole parabola sideways, we would get, I'm not gonna put it on my paper because I don't want you to copy it down, but if I turn that whole parabola sideways and included the bottom half, then that wouldn't be a function. It wouldn't pass the vertical line test. That's why we only have to use the top half would be a function or the bottom half would be a function. The next graph is f of x equals x cubed. The domain, the numbers that you can cube, are from negative infinity to infinity. Cube anything in the whole wide world. I'll go back to my -2, -1, 0, 1, and 2. Cube each one of those x's. And then graph those ordered pairs. By the way, if on the test I give you a grid for a graph, let's say it has tick marks and all that good stuff. If you have to graph a point outside the grid, just make your own tick marks. I'm not terribly picky on these graphs. Again, the reason that we're learning them is so that if we go on to calculus and use a graphing calculator, we know what the basic shape is before we enter it on the calculator. So if you have to add some more tick marks to any of my graphs, that's fine. Here's the point -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. And before I connect these, this illustrates why you can't just use 2 points or sometimes even 3 points to get a good picture of the graph. If I had just used -1, 0, and 1, I may have thought that this was a linear function. I could connect those 3 points with a straight line. It's not until I pick some x's farther out to the left and the right that I realize, oh, that's not a line. It's very steep downward to the left and very steep upward to the right. That's the graph of our cube function. And again, just to give it some words that I can describe what that graph looks like. You won't find this in any college algebra book or any book, but if I say vertical snake, if I say the cube function looks kind of like a vertical snake, I want you to have that image in your head. The cube root function. What numbers can I take the cube root of? Well, I can only take the square root of positive numbers, but I could take the cube root of positive or negative numbers. So I'm going to choose, well, let me write the domain first. It's negative infinity to infinity. I can take the cube root of anything. And I'm going to choose my x's to be some perfect cubes so that I can take the cube root without having to punch it on my calculator. my first few perfect cubes in the negative direction. Let's say -8 is a perfect cube, -1 is a perfect cube, 0, 1, and 8 are all perfect cubes. And then just take the cube root of each of those. Cube root of -8 is -2. Cube root of -1 is -1. Cube root of 0 is 0. Cube root of 1 is 1. And the cube root of 8 is 2. And just like the square root function was this function turned sideways, but we can only use half of it, so that we would still have a function. The graph of the cube root function is the vertical snake turned sideways. I'm not even going to make tick marks for this. I'm just going to turn that x cubed sideways and call it a horizontal snake. Now, something that we will talk about more if you go into pre-calculus, but I just want to point it out now. These two functions are called inverses of each other. If you cube a number and then take the cube root, you get back the original number that you started with. Anytime you graph a function and its inverse, all the ordered pairs are reversed. The y values on our table for x cubed are my x values on my table for cube root of x. And my x values for x cubed are my y values for cube root of x. All the ordered pairs are reversed, and that's what causes the graph to be flipped sideways. All right, two more. F of x equals absolute value of x. What's the domain? What numbers can you take the absolute value of? Well, you can take the absolute value of anything. So the domain's -infinity to infinity. So pick some negative x's and some positive x's. And take the absolute value of each of those x's. And then graph those 5 ordered pairs. -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. That would look a lot like the shape of a parabola. I'm going to tell you how you know that this is not a curve at the bottom, but a sharp turning point. We're going to say the graph of an absolute value function, and specifically, I have to be precise because I'm a teacher, specifically I'm going to say the absolute value of a linear expression, a first degree expression. The graph of absolute value of a linear expression is V-shaped, and here's why it is V-shaped. The definition, the official definition of absolute value of x is a piecewise function, and we talked about piecewise functions. The two pieces of this graph are x is greater than or equal to 0 and x is less than 0. That's the domain of the absolute value function, all the 0 and positive numbers, all the negative numbers. If I put a positive number into the absolute value function, I get out the same thing I put in. If I put in a 7, I get out a 7. If I put in a 0, I get out of 0. So the first part of this graph is y equals x, as long as you put in 0 or positive numbers. But if you put a negative number into the absolute value function, you get out the opposite of what you put in. And I gotta sneeze. Excuse me. excuse me. Put in a positive, you get out the same thing you put in. Put in a negative, you get out the opposite of what you put in. This piece of the graph of the absolute value function is y equals x. It's this piece of the identity function. This is the graph y equals x. And this is the graph of y equals negative x. So it's V-shaped because it's where these two half lines, or in geometry we call them rays, it's where these two rays meet, and they meet at a point, not a nice U shape like parabola. All right, one more. And for this one, I had no idea what f of x equals 1 over x looks like. So I had to pick a whole bunch of x's. And I chose negatives, and I chose positives, and I chose 0, and I chose fractions between 0 and -1, between 0 and +1. Again, once you get the basic idea of the shape of this function, you're not going to make an XY chart at all. You're just going to know what the reciprocal function looks like. The reciprocal function takes any number you put in and takes the reciprocal or flips it. If you put in a 5, you get out a 1/5. If you put in a 1/3, flip it, you get a 3. What's the domain of that function? We talked about the domain of a fraction is all numbers except what makes the denominator 0. The domain of this function is all values of x except 0 or not equal to 0. Now that can be written in interval notation. -infinity to 0, not including 0, and then 0 to infinity, not including 0. That's the union symbol between those two intervals. It just means the domain is all of these numbers and all of these numbers. X is not equal to 0 is just an easier way to write it. All right, let's make this tape. The reciprocal of -3 is -1/3. The reciprocal of -2 is -1/2. The reciprocal of -1 is still -1. You flip a 1 and it's still a 1. You flip a -1/2, -2. Flip a -1/3, it's -3. Notice the reciprocal function doesn't change the sign of the number, it just flips it. And I put 0 on my XY chart, but we've already made a note that we can't put a 0 into the reciprocal function. I'm just gonna try to squeeze in at least part of the word undefined. That function's undefined when x is 0. The reciprocal of 1/3 is 3. The reciprocal of a 1/2 is 2. The reciprocal of 1 is 1. The reciprocal of 2 is a 1/2. And the reciprocal of 3 is 1/3. So I'm going to be quiet for a minute and let you graph all of those ordered pairs. Looks like we have 10 ordered pairs to graph. And I would make my x's, I would make my tick marks kind of spread out because I have to graph little bitty fractions like x is a 1/2 and x is a 1/3. I'm going to widely space those tick marks. These first 5 ordered pairs are in the 3rd quadrant. where your x's are negative and your y's are negative. These last 5 ordered pairs are in the first quadrant, where your x's are positive and your y's are positive. And I can connect these 5 points with a smooth curve. I can connect these 5 points with a smooth curve. Should these 2 curves be connected somehow? Maybe a squiggly line or a diagonal line? No, they can't be connected. If I cross the y-axis, that's where x is 0. And we said x can't be 0. So this graph can't cross the y-axis. It's 2 different pieces of the function. And like I said, I could make a nice smooth connection for these 5 points and for those 5 points, but I need to keep thinking about what happens as x gets infinitely big. As I flip numbers that are bigger and bigger. I flip a 10, I get 1/10. If I flip 100 way out here off the paper, I would get 1/100th. What are those y's getting close to as x's get infinitely big? 1/10th, 1/100th, 1/1000th, 1/10,000th. Those y's are getting closer and closer to 0, but they're never going to be 0, and they're certainly never going to be negative. You're not going to get a negative from flipping a positive number. The same thing happens to the left of the graph as you take the reciprocal of smaller and smaller negative numbers. Since we're going to the left, I'm going to say smaller and smaller negative numbers. You get numbers closer and closer to 0 again, but they're never going to be 0, and they're never going to be positive. They're not going to cross the x-axis. As I flip numbers that are getting closer and closer to 0, flip a -1/2, I get -2. Flip -1/3, I get -3. Wait, I said from the right. Flip a 1/3, I get a 3. Flip a 1/2, I get a 2. If I flipped a 1/10th, I get 10. If I flipped 1/100th, I get 100. So as this graph is getting closer and closer to x equals 0 from the right, my y's are taken off to infinity. And as my x's get closer and closer to 0 from the left, my y's are taking off to -infinity. So that's the graph of the reciprocal function. It's important to note that you can't let x be 0, and that the 2 pieces of the graph are in the first and third quadrant. Again, because if you flip a positive, you get a positive. If you flip a negative, you get a negative. Let me just show you some notation that we will use in calculus. And if you're not going on to calculus, it's okay. It's not going to hurt you to learn this. As this is the notation for as x gets infinitely big, as x goes to infinity, my y's approach 0. As x gets infinitely big, my y's approach 0. As x gets infinitely small, as x goes forever to the left, my y's approach 0 also. When you have a line, a horizontal line, that the graph gets closer and closer to as x goes to either -infinity or +infinity, that horizontal line is called a horizontal asymptote. Horizontal asymptote for the reciprocal function is y equals 0, better known as the x-axis, because that's the horizontal line the graph is approaching as x goes to +infinity or negative infinity. We'll talk more about asymptotes later. That's all I want to say about them right now. All right, so there are my 8 basic functions. And if you need to put them on flashcards, that would be a great way to check and make sure that if you saw the function, you would have the instant mental image of that function in your head. Put y equals x squared on the front of a flashcard and this on the back of the flashcard. Put y equals cube root of x on the front of a flashcard, put a horizontal snake on the back of the flashcard. You need to know what these basic shapes are. And I'm going to say most of them have, let's say, do something important. There's more mathematical language for that in calculus, but I'm going to say most of these do something important at the origin. Y equals x goes through the origin. Y equals x squared. That later we're going to call that turning point of the parabola, the vertex of the parabola. It's at the origin. The square root of x starts at the origin. The cube function goes through the origin, and that's where the curvature changes. Same thing for cube root of x and for absolute value. 0, 0 is an important point on all of those graphs. Not necessarily the horizontal line. It may not go through the origin, and certainly the reciprocal function can't go through the origin, but all of the rest of these go through the origin, and something important happens at the origin. We're going to call 0, 0 the critical point for all of these graphs. And it's important, in calculus, there will be a more formal definition of critical point, but now we're just going to say it's the point where something interesting happens, where the curvature changes or where the graph starts. Calling that a critical point will allow me to describe what I'm doing to a graph that has been shifted left, right, up, or down, and that's the next thing we're going to talk about. Transformations of graphs. Now, I like this section because in the beginning, it may feel like, what the heck is going on and how did she know that? I can almost guarantee every one of you will be have this light bulb come on by the time we finish our examples in this section. You'll understand what moves a graph left, right, up, and down, or what flips it upside down. Moving a graph left and right, that's called a horizontal shift. If we start with some basic function, f of x, and we subtract something before we apply the function, what we've subtracted is our horizontal shift. For example, this x minus 2 squared, the parent function, if you want to call it that, the original function, just y equals x squared. As soon as I say y equals x squared, I know it looks like this, but that 2 has shifted this function. And for reasons I'm not going to make clear for just a minute, and I will, I'm going to choose 0, 1, 2, 3, and 4 as my x's. Each one of those x's, when I put it into the function, I subtract 2 before I square that value. 0 minus 2 is negative 2. Negative 2 squared is 4. 1 minus 2 is negative 1. Negative 1 squared is 1. 2 minus 2 is 0. 0 squared is 0. 3 minus 2 is 1. 1 squared is 1. 4 minus 2 is 2. 2 squared is 4. When I graph these ordered pairs, I expect to get a shape just like y equals x squared, but I'm going to see that it shifted. 0, 4 on the y-axis. 1, 1, 2, 0, 3, 1, 4, 4. There's my parabola. And if I ask you how that parabola has been shifted in comparison to our basic parabola, you would say it's our basic parabola just shifted to the right 2. Two things I want you to notice. Number one, that 2 is subtracted before the squaring. That's why it's the horizontal shift. In just a minute, we're going to say what's added or subtracted after the function. That's your vertical shift. But right now, we're only focusing on the horizontal shift. Subtracting 2 actually moves the graph to the right 2. So we're going to say that horizontal shift works the opposite of what you expect. If subtracting 2 moves the graph to the right 2, then on this second example, adding 1 in the absolute value function will move the graph to the left 1. That 1 is added before you take the absolute value. That's why it's a horizontal shift. And that horizontal shift is always the opposite of what you would expect. So I'm going to speed up just a little bit. I'm not going to fill out that XY chart. I'm just going to say that I know the basic graph of absolute value of X is this V shape. This graph is just this graph scooted to the left 1. That's where its turning around point's going to be, or its critical point. So I'm just going to make that critical point at -1 instead of 0, and then attach my nice smooth V-shaped graph that turns around at -1. And you'll notice on both of these examples, the critical number is the horizontal shift. If this graph is shifted to the right 2, then the critical number is 2. This graph is shifted to the left 1, the critical number is -1. So horizontal shift is what's added or subtracted before you apply the function. That's inside the parentheses or inside the absolute value or under the radical, whatever the function is. Vertical shifts are achieved by adding or subtracting something after the function is applied. For example, y equals square root of x plus 3. That if I ask you to evaluate that for x equals, let's say 0, or for x equals 4, you would take the square root of 4 before you added the 3. The 3 is added after, which is what makes it a vertical shift. Maybe I'll highlight 2 things for you. The horizontal shift is what you subtract before you apply the function. The vertical shift is what you add after you apply the function. So in this first example, I'm going to pick some perfect squares, so I don't have to use my calculator. And the smallest perfect or smallest number I can take the square root of is 0. So maybe I'll choose 0, 1, 4, and 9. Take the square root of each of those numbers and then add 3. Square root of 0 is 0. 0 plus 3 is 3. Square root of 1 is 1. 1 plus 3 is 4. Square root of 4 is 2. 2 plus 3 is 5. And the square root of 9 is 3. 3 plus 3 is 6. I want to plot those 4 ordered pairs. I know what the general shape of the square root of x looks like. It's this top half of a sideways parabola. I'm Gonna write that out to the side. Y equals square root of X looks like this. And so I'm gonna plot those 5 ordered pairs. 0, 3, 1, 4, 4, 9, and way out here somewhere would be 9, 6. I'm going to connect those points with the shape that I know the graph of square root of X has. Supposed to look like a top half of a parabola. And if I said, how is this graph a transformation of this graph? You'd say it's just this graph shifted up 3. And notice 3 is what was added after we took the square root of each number. So this graph shifted up 3 is the graph of this function. Now, the critical number up here, I said the critical number is your horizontal shift. It's what's added or subtracted before you apply the function. Well, this one doesn't have anything added or subtracted before we took the square root, so its critical number is still 0. And the same thing for this second example. Nothing is added or subtracted before I square the X, so the critical number is 0. That 4 is subtracted after I square the X, so I'll get a parabola, but it's been shifted down 4. And again, just to save a little bit of time, I'm not going to fill out that XY chart. I'm just going to take my basic parabola and shift it down so that its vertex is at -4 instead of 0. A good enough mental image so that if you punched it wrong on your calculator, or if your calculator was really zoomed in, if you were really zoomed in to just this piece of the graph, you could think it was a vertical line. But you would know that X squared is not a vertical line, and you would zoom out until you could see the whole parabola. All right. There's one other thing, one other transformation that we're going to talk about. There are some others we're not going to talk about just for time's sake and because our goal here is quick mental image. It's not a beautiful, detailed graph. In some other sections, we're going to talk about more beautiful, detailed graphs, and I will ask you more questions. I will ask you, what's the x-intercept? What's the y-intercept? What's this and that? That's not our goal here. Our goal is to recognize the basic shape and how it's been shifted left and right, or up and down, or what causes it to flip upside down. For example, y equals negative absolute value of x. Nothing has been added or subtracted before you take the absolute value. Nothing has been added or subtracted after you take the absolute value. So this V shape still turns around at 0, 0. There's no horizontal shift or vertical shift. What that -1 does, we'll do one XY chart. Let's choose, say, -2, -1, 0, 1, and 2. If I let x be -2, the absolute value of -2 is +2. But then I'm going to write this as -1 times the absolute value of x, so that you can see I take the absolute value and then multiply it by -1. Absolute value of -2 is +2. Then multiply it by -1, and I get -2. Absolute value of -1 is 1. Then I multiply it by -1. I get -1. And I'm just going to finish this. You can verify each of those y's for yourself. Now I'm going to graph those ordered pairs and see what's happened to the graph of my absolute value function. -2, -2, -1, -1, 0, 0, 1, -1, 2, -1. This graph is still V-shaped, but it's upside down. That's what we call a reflection, a flipping across the x-axis. And that happens whenever you put a negative coefficient on your function. If I graphed negative x squared, it would just flip this parabola upside down. If I put negative x cubed, it would flip that vertical snake so that it was going downhill instead of uphill. Actually, that's what this example 2 is. X cubed, y equals x cubed is this nice smooth uphill snake. So y equals negative x cubed flipped across the x-axis is that nice smooth downhill snake. And one more time, just to make it very clear, I'm not expecting big XY tables. Actually, you can always use an XY table. If you blank out on the test, you just forget what a shape is, you can use an XY table. But if you have studied these 8 basic shapes and what shifts them left, right, up, or down, you don't need big XY tables for these basic functions. And that's what the goal of this section is. So let's talk about all of those different transformations put together. And the next page of your notes, I just have 10 functions that when we start out, you may not feel comfortable with it, but I'm hoping by the time we get to number 4, you can just look at it, you can tell me the basic shape, you can tell me the critical point, and you can graph it. Now, when I said critical number, I was just referring to the horizontal shift. Here, when I say critical point, I'm not just talking about the horizontal shift, I'm talking about the horizontal shift and the vertical shift. I'm talking about an ordered pair. So, number 1, I know the basic shape of x squared is this concave up parabola that turns around at 0, 0. You don't have to graph that in your homework or on the test, but if I don't put it on my paper, you can't see the picture in my head. So this is the picture in my head. Then I'm thinking, what's subtracted from x before I square it is a horizontal shift. There is no horizontal shift. There's nothing added or subtracted before you square. So the horizontal shift is 0. See if I can make this a little, show up just a little. Ooh, not that way. Ah, there we go. That's better. Your horizontal shift is 0 because nothing is added or subtracted before you square the x. That 2 is added after you square the x, so it's the vertical shift. If you tell me on the test, if you tell me the critical point is 0, 2, 0, 2 right here, and that's the point where the parabola turns around, that's all I'm looking for. I don't care how wide you make your parabola, how narrow you make your parabola. If I cared about that, I would get you to pick some more points to get the exact width correct. But here, I just care about you knowing this shape and this critical point where that graph turns around. All right, example 2, y equals x cubed. That's the parent function, and I know that basically it's that uphill snake. So that's the picture I have in my head. The horizontal shift is what's subtracted before I cube the x. There's nothing inside parentheses subtracted before you cube the x. So the horizontal shift is 0. That -1 is your vertical shift. So the critical point's 0, -1. Just plot that critical point. Ooh, I like to call for a vertical snake, I like to call that critical point the snake's belly button, as if my husband wasn't a wildlife biologist and I didn't know snakes don't have belly buttons. It still helps me think that's where the curvature changes. In calculus, we would say it's an inflection point, but in college algebra, we're just going to call it snake's belly button. All right, number 3, I know what the basic square root function looks like. It's that half of a sideways parabola. And the critical point is that 1 a horizontal shift or a vertical shift? It's you add 1 to x before you take the square root. It's inside the function, so it's a horizontal shift. And you have to remember that horizontal shift always works the opposite of what you expect. Adding 1 before you take the square root actually moves the graph to the left 1. So my horizontal shift is -1. And there's nothing added or subtracted after I take the square root. There's no vertical shift. That means the critical point is -1, 0. So if you plot -1, 0, and starting there, attach that half a sideways parabola, that's good enough. That's all I'm looking for. All right, number 4, I know what the basic x cubed function is. That vertical snake. That 2 is added to x before we cube that. So it's my horizontal shift, and that horizontal shift always works the opposite of what I expect. So this is a shift to the left 2. And then my vertical shift is down 3. If we started at 0, 0, went to the left 2 and down 3, that's our critical point, -2, -3. The horizontal shift and the vertical shift. And I expect this vertical snake with the belly button at -2, -3. If I wanted you to be more precise, I would ask you more questions. All right. Now, I said by number 4, your light bulb should come on. If I had a live class in front of me right now, I would ask, is your light bulb on? Are you understanding how to get the basic shape and the critical point? If you're struggling with that, we're going to have a few more examples, but then you may need to email me. Let me know if you need help with that. All right, number 5. It's my basic y equals square root of x function. I know my square root of x function is that top half of a sideways parabola. And this hasn't been shifted horizontally or vertically. There's nothing added or subtracted before you take the x. There's nothing added or subtracted before you take the square root of x. So the critical point, the horizontal and vertical shift, is 0, 0. That's still where this graph is going to begin. But that negative coefficient reflects WRT, stands for with respect to, because it would take a minute to write that, reflects with respect to the x-axis, which just means flip it upside down. Instead of the top half of a parabola, it's the bottom half of a parabola. Now, on number 6 and 7, you're going to see something other than a horizontal and vertical shift. For example, number 6, your horizontal shift opposite of the guy inside parentheses, to the right 2, and this vertical shift is up 1. So I'm going to say the critical point for this function is 2, 1. And I know that the basic graph, y equals x squared, is this parabola. This parabola is being shifted to the right 2 and up 1. This 3 definitely affects the graph, but it affects the width of the graph, how wide or narrow it is. If I wanted the exact width, I'd have you choose some more x's or y's. Choose some more x's, find some more y's. Because I'm not looking for that level of precision, if you just plot the point 2, 1, and then put a parabola that turns around right there, I don't care about the width. I'm not saying that 3 doesn't matter. It doesn't affect the graph. I'm not saying that at all. I'm saying it doesn't matter to me right now, because all we're going for is right shape, right critical point. Same for number 3. I know that y equals absolute value of x is that nice V-shaped graph that turns around at the origin. And I know that this graph has been shifted. My horizontal shift is that 1 that's added inside parentheses, but it works the opposite of what you expect. And then down 3. So my critical point, 1 to the left is -1. Down 3 is -3. My critical point is opposite of the guy in the absolute value and the guy on the end, -1, -3. -1, -3 is right here. I don't really care about the width of this V-shaped, or I would pick some more X's and find some more Y's. If you just have the V-shape that turns around at -1, -3, that's all I'm looking for right now. All right, 3 more. Number 8. I know that the graph of y equals cube root of x. Y equals cube root of x is that horizontal snake. The critical point of this function is +2, +3, opposite of the horizontal shift and the vertical shift. I shouldn't only say opposite of the horizontal shift. The horizontal shift is to the right 2, and then the vertical shift is up 3. So the critical point is 2, 3. That horizontal shift is always what's subtracted from the x, and that's a +2 that's subtracted from the x. Here it was a, well, let's see. Here it's a -1 that's subtracted from x. That means the critical point's at -1. All right, back to number 8. 2, 3 is right here. And that's the horizontal snake's belly button. If you don't tell my husband I said that. All right, number 9. I know the basic graph of y equals x cubed is this vertical snake. And turns that the curvature changes at the origin. But I know this graph has been shifted 3 to the right. It's the horizontal shift, and down 2, that's the vertical shift. So my critical point is 3, -2. Opposite the guy inside the function, inside the parentheses, and then the guy added or subtracted on the end. 3, -2. And vertical snake with that at its belly button. Ooh, I just noticed something. I was paying such close attention to my horizontal and vertical shift that I didn't see that for a minute. What does that negative coefficient do to this graph of x cubed? Flips it upside down. Y equals negative x cubed is a downhill snake. So I have made a mistake. I need white out to tape. If not, I'll just scribble it out. Ah, there we go. 3, -2 was right here. I should just have a downhill snake through that. By the way, on the test, some folks give me snakes that are neither horizontal or vertical, and I don't know what's going on. I get some graphs that look like this. That's not even a function. It doesn't pass the vertical line test. Here's a vertical line that touches that graph in 3 places. So your graphs for this section should not look like an S. It's either vertical, clearly vertical, or clearly horizontal. All right, last one of these. It's the cube root function. Y equals cube root of x. I know that that is the horizontal snake going uphill from left to right. And I know that that negative coefficient is going to flip that with respect to the x-axis so that it's going downhill left to right. I can see that the horizontal shift is to the left 1, and the vertical shift is down 3. So the critical point is opposite of the guy inside the function and the guy outside the function. -1, 3. I'm sorry, -1, -3, because it's down 3. Plot that ordered pair -1, -3. And then make sure you graph negative cube root of x going downhill instead of positive cube root of x. Make sure it's clearly a horizontal snake, not some kind of drunk snake. Ooh, having a little trouble with that one. All right. Now, unfortunately, since you do your homework in MyLabs, MyLabs doesn't have great graphing tools for all these different kinds of functions. Some of the problems, it gives you a multiple choice graph, and certainly I'm not going to make this multiple choice on the test. So what I've done for you, because I love you, is in your notes, I've given you an extra page of practice. It also has 10 problems. They're different than the 10 that we just did. And I gave you the answers for those. So in addition to doing the homework, I would definitely do these 10 extra problems. And probably before the test, I'd do them again, just to make sure that I had the basic shapes and knew how to find the critical points. All right. There is one last thing in the homework, and it is piecewise functions. Piecewise functions are defined by different expressions. Should have made that blank bigger. different expressions on different parts of its domain. Domain is what x can be, and for different parts of the domain, the function's defined to be different things. For example, this is a piecewise function. It has 3 parts. For all the x's less than 0, in other words, if I put in a negative number, I square it to get the y. If I put in a 0, this function is just going to spit out a 2. And if I plug in a positive number, this function is going to add 2 to it. So what's the domain of this function? What are the x values for which the function's defined? Well, it's defined for all negative numbers. It's defined for 0. And it's defined for all positive numbers. So the domain is negative infinity to infinity. It's not the same expression for every part of its domain, but it is defined from negative infinity to infinity. Finding some function values. If I want to find f of -2, I look to see which part of the domain that falls into. When x is -2, that's a negative number. And this function says if I put in a negative number, then the y value is that squared. -2 squared, or +4. Find f of 0. I look to see in which part of the domain that value falls. Well, it's the middle part. It says when x is 0, your y is just 2. I don't have to do anything to it. When I plug in a 0, this function gives me a 2. And when I put in a 3, well, that's a positive number. So the function returns 3 plus 2, or 5. So that's how you find function values for piecewise functions. And now we want to graph a piecewise function. You know what this part of the graph is going to look like? Y equals x squared is going to be a concave up parabola. All the x's that are less than 0 is just the left-hand side of that parabola. The middle of the graph is going to be the point when x is 0, y equals 2. So it's just going to be a dot. And then for all the positive numbers, y equals x plus 2. That's a linear expression. So that piece of the graph is going to be a line. One other thing I can tell you just by looking at this, x is less than 0 does not include 0. On my graph, I'm going to show that with an open dot on 0. And x is greater than 0 doesn't include 0. So I'm going to have an open dot on 0 there. That's just my quick mental image of what the 3 pieces of this graph look like. A parabola, a point, and a line. To figure out where they go on my graph, I'm going to use a table. You may get to the point where it's not necessary to use a table, but for our first one, certainly we need to make a table. And I'm going to choose some x's from this part of the domain, some x's that are less than 0. Let's say -3, -2, -1. And then I'm going to let x be 0. Well, I already know what y is when x is 0. And then I'm going to choose some positive x's, maybe 1, 2, and 3. When I'm plugging in negative x's, I'm going to square them. -3 squared is 9. -2 squared is 4. -1 squared is 1. When I plug in these positive x values, I'm plugging them into the last part of this function. You know what? I think I'd like to write in this gray area for x is less than 0. That's the first piece of that function. And then for x is greater than 0, that's the last part of this function. So the last part of the function, I'm going to add 2 to each x. 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5. And then I'm going to plot all those ordered pairs. -3, 9 goes off my chart just a little bit. -2, 4, 3, 9, kind of in the wrong place. It's more there. -2, 4, -1, 1. That's my first 3 ordered pairs. And then 0, 2 is that middle dot. And then 1, 3, 2, 4, and 3, 5. All the x's greater than 0, I can see that line that I was expecting, that line with positive slope. But numbers that are bigger than 0 don't start at 1. They actually go all the way up to 0 and don't include 0. So I don't need to stop that portion of the graph at 1. I need to say, if I continue that line all the way to 0, that would have an open dot on the 2, except for this tells me to have a closed dot on 2. It's like a closed dot on top of an open dot. It becomes just an open dot. 0, 2 is on that graph, and it's also on the left side of this line. Now, I don't know why I said left side. That's the right side of that line. Y equals x squared. We know it's a parabola. I can connect these 3 points in kind of a parabolic shape. But all the numbers that are negative don't stop at -1. They all go all the way to 0. So I need to make that parabola go all the way to 0, but not include the 0. And that's my half a parabola with an open dot on the end. That's my 0.02 with a closed dot. And that's my half a line, which would have an open dot, except for it's already filled by this point. And the range of this function ranges lowest y value to highest y value. The lowest value goes all the way to 0, but doesn't include 0 because there's an open dot. In interval notation, I show that with a parentheses. 0, starting at 0, but not including 0, and then the graph goes forever up. So the range of that graph is 0 to infinity. All right, we have one more example. Oh, darn it, we have 2 more examples. One more graph and then one application. So what about this graph? Example 2 is also a 3-part piecewise function. It's defined to be -2x plus 1. If I put in any x's between -3 and 1, including the -3, because that equals not including the 1. If I put in a 2, it just gives me x equals 1. And if I put in anything bigger than 1, it gives me x squared. I'm not sure if I said this middle part correctly. What I meant to say, I don't know if it's what I did say or not. What I meant to say was when x equals 1, y equals 2. And then the last part, when x is bigger than 1, y equals x squared. I know what the 3 pieces of this graph look like. negative 2x plus 1 is a line. And specifically, it has a negative slope. So I know this part of the line goes downhill from left to right. It starts at negative 3. So this left end is going to have a closed dot on it because negative 3 is included. The right end is going to go up to 1, but not include 1. So I'm going to have an open dot when I get to that value where x is 1. This middle is just a point again. When x is 1, y is 2. That's just a point. And then for all the x's greater than 1, y equals x squared will be a parabola. And for that parabola, it doesn't include the 1. So I'm going to have an open dot on the 1, and the parabola is after that. That's my mental image of what the graph looks like. Now, example 1, the graph went from all the x's smaller than 0 to all the x's bigger than 0. Our domain was negative infinity to infinity. In this one, the x's only go to negative 3 and stop at negative 3. So the domain of this function begins at negative 3, including the negative 3, and then does go forever to the right. X is greater than 1 has no end. So we say the domain is negative 3 to infinity, including the negative 3 because of that equals. F of negative 2, well, which part of the graph does that fall into? Negative 2 is between negative 3 and 1. So I'm going to use this part of the function. Negative 2 times the value of x, which is also negative 2, plus 1. I just put negative 2 into that expression, and I got negative 3. F of 1, this middle part tells me when x is 1, I don't have to do anything. It's always going to spit out a 2 for the y value. And f of 2 is the third part of this domain where the expression is the square of whatever I put in. If I put in a 2, it spits out a 2 squared or a 4. All right, I want to graph the function for all the x's between negative 3 and 1, including the negative 3. That portion of the graph is y equals negative 2x plus 1. And then for all the x's greater than 1, that's this piece of the graph where the y's are the square of the x's. And of course, the middle part is when x is 1, y is 2. So I'm going to pick some x's between negative 3 and 1, including the negative 3. Maybe I'll choose negative 3, 0, and since this goes all the way up to 1, but doesn't include 1, I'm going to go ahead and put 1 on my XY chart, but make myself a note that that point's going to be an open dot. All the x's between negative 3 and 1 go all the way up to 1, but don't include 1. So I'm going to have an open dot on that point. All the x's greater than 1. Well, again, you can't say all the x's greater than 1 start at 2 because 1.5 is bigger than 1. I've got to go all the way up to 1, but not include it. So I'm just going to say that is going to be an open dot as well. And then I'm going to pick some other x's that are bigger than 1. These 3 x's I'm going to plug into this expression. Negative 2 times negative 3 is 6. 6 plus 1 is 7. Negative 2 times 0 is 0. 0 plus 1 is 1. And negative 2 times 1 is negative 2. Negative 2 plus 1 is negative 1. I'm going to have an open dot on the ordered pair 1, negative 1. And then for the third part of this function, I'm going to square these three x's. And I've made myself a note that 1, 1 is going to have an open dot on it. So let's plot these points, negative 3, 7, right there, 0, 1, and 1, negative 1 with an open dot on it. And that piece of the graph we already knew was going to be a line that was sloping downhill with a closed dot on the left end and an open dot on the right end. So here's the first piece of this graph. And the middle part, when x is 1, y is 2, that is this ordered pair right there. And then the last piece of this graph starts at 1, 1 with an open dot on it. And with an open dot. And then 2, 4, 3, 9. And that's a pretty wonky parabola. But if your graph, if I can tell that's a piece of a parabola, not a line, it's good enough. We're asked to find any intercepts, any points where the graph crosses either axis. Looks like this graph crosses the x-axis in one place and the y-axis in one place. The x-intercept, you'll remember from our section on, well, I think the last lesson, lesson 3, we said to find an x-intercept, you let y be 0, and to find a y-intercept, you let x be 0. Y is 0 right about here. Instead of guessing what that might be, I'm going to actually go to that part of the equation and let y be 0. If I let y be 0, I'd have to subtract 1 from both sides and divide both sides by negative 2. I get x is a half. When y is 0, x is negative a half. And then when x is 0, I can see where the graph crosses the y-axis exactly at 1. So those are my two intercepts. And then for range, the graph, the lowest y value would start at negative 1, but negative 1's not included. I'm going to show that with a parenthesis on negative 1. And then it does go forever up, and it includes all the values from negative 1 to 1, all the y values from negative 1 to 1. No, I'm sorry, all the y values from negative 1 to infinity. So the range is negative 1 to infinity. All right, it's been a long lesson. We only have one more example, and that's the application. A good application of a piecewise function is car rentals, because when you rent a car, this is actually a lease, a 4-year lease. The company charges $8,450 just for you to drive it off the lot. That's your basic lease amount. And with that, you get up to 10,000 miles. If you drive more than 10,000 miles, then they start charging you a mileage charge of 30 cents per mile. So if we write that, well, let's do the A and the B part, and then we'll figure out how to write that as a piecewise function. The cost of a 4-year lease, if you drive the car 7,000 miles. Well, if you drive less than 10,000 miles, you don't have to pay this extra fee. You just have to pay the 8,450. But if you pay 13,000 miles, you are going to have to pay this fee. You don't have to pay this fee on the whole 13 miles, though. You just have to pay this fee on the amount you drive past the limit. The limit's 10,000 miles. So 13,000 miles would be 3,000 over the limit, I guess is the best way to say it. So you're only going to have to pay the 30 cents a mile on this 3,000. You're still going to have to pay that 8,400 for those first 10,000 miles. And then you pay 30 cents per mile. Oops. 30 cents per mile for these other 3,000. So your mileage charge would be $900. 30% of 3,000 is 900. In other words, if you drive 13,000 miles, you're going to have to pay $9,350. It's important to notice you don't pay that extra mileage fee for all the miles you drive, just the miles over 100. Excuse me, the miles over 10,000. So you have one expression for up to and including 10,000 miles. You have a different expression if you drive over that. So my, if X is the total number of miles driven, then you could write the function, let's use C of X for cost. That kind of makes sense instead of using F of X. F of X would be fine. C of X, I just get what it's about. It's a piecewise function that has two pieces. The first piece is for X miles up to 10,000. So for X less than or equal to 10,000, what do I pay? If I drive less than or equal to 10,000, I only pay this $8,450, and that's it. But the second part of the function is when X is greater than 10,000, and I still have to pay the 8,450, but then I have to pay that 30 cents a mile times the number of overage miles, if you want to call it that. 30 cents per mile is, I haven't left my here. $8,450 plus 30 cents per mile. Is that just 0.30 times X, 0.30 times however many miles you drove? No. You only pay that 30 cents a mile on the miles over 10,000. When we drove 13,000, how did we find this 3,000? Well, how many miles above 10,000 is 13,000? Subtract. 13,000 minus 10,000 is how we got this 3,000. So if X is the number of miles driven, then I'll just write this as a note at the bottom. X minus 10,000 is the number of, I'm gonna call it overage miles. That looks like average, but it's not, it's overage, the amount over the limit of 10,000. So this 0.30 isn't multiplied by X, it's multiplied by X minus 10,000. You subtract 10,000 from the total number of miles you drove. You multiply that times 30 cents, or yeah, 30%. And then you add that flat fee of 8,400. That's the second part of your function. I would bet in MyLabs, they would want you to go clean that up, go ahead and distribute the 0.30x and combine like terms. But since I didn't leave myself room to do that, we'll stop right there. And the homework is assignment 4, the library of functions and transformations, and piecewise functions. I just don't have that as part of the title. Alrighty, thanks for watching, and just email me if you have any questions with the homework. I'll be glad to help.